I am now so turned on.
This is why
That's not a pretty picture. Thank you all for coming and for having us stand between you and drinks. Since you shouldn't drink, we're going to take forever. We'll have a drink with you. So this is Khawaja Shams. He's now a rocket scientist. I am Tom Soderstrom. I'm the Chief Technology Officer at NASA's Jet Propulsion Laboratory. We're also a Caltech. We're also a federally funded research center. Just ask me and we'll spin. We'll be anything you want us to be. But what we are is we do lots of computing. And what we're wanting to talk to you about today is this is the thesis right here. What was science fiction yesterday is evolving into today. It's now reality, on the edge of reality. But what is it going to be tomorrow? And cloud has everything to do with this. So that's the journey we're going to take. So we will start by talking about science fiction yesterday, then how we're evolving, where is the edge of reality, and where it's going. And we will leave time for questions so you can ask all your technical questions then. What we wanted to do is lift it up a little bit. Cloud is not just about servers. It's not just about storage. It's a whole lot more. It is taking us into the future. Did you see the keynote this morning? Do you want to drive that rover on Mars? Khawaja can get you there. So Khawaja, let's talk about what was science fiction yesterday.
All right, so the high-level description of science fiction yesterday, we always try to draw a parallel between us in 1880. So imagine yourself prior to any time before 1885. And then put yourself in the shoes of a small business owner. And a small business owner whose business relies on electricity to generate the products that you need to sell. And in this business owner's mind, if you were given a large, in 1880s, you were actually generating your own electricity if you wanted to run the small business. And putting yourself in the shoes of the small business owner, if you were given a large order right around Christmas time, you had two options. Okay, you can go make a capital investment in a larger generator, wait for the generator to be arrived, wait for the installation to be done, wait for the calibration to be done, maybe go even out for a little bit, have some outage to do the installation process. Or you can refuse the business, right? Because technically, you're going to make this capital expenditure, and then this generator is basically going to sit idle for the rest of the year until hopefully next Christmas you'll get the same amount of business again. Now, in 1885, Thomas Edison transformed the way we approached electricity. Thomas Edison opened the gates in 1885 to the Pearl Street Power Station. And with the power station, he allowed us to think of electricity as a consumable commodity. He allowed us to think of it as something that we can get on demand as much as or as little as we need, and to get and pay for as much as we use, right? And it's the same model. He basically did modern plumbing for electricity, and it allowed us to think of electricity the way we think of modern plumbing. Cloud computing to NASA, to us, is that same model applied to your compute, storage, and network needs. It is the ability to provision capacity on demand, get it as quickly as you need it, turn it off, and stop paying for it when you're done with it. That's what cloud computing is to JPL.
So just like that was science fiction in 1880, in 35 years ago when we launched, what spacecraft is this? Voyager, all right. We got some old people in here. It was science fiction. And in fact, it broke within a few years. So what do? We reprogrammed the thing over and over and over and just extend its life. So that's part of the story here, is to how do we keep evolving? But it entered a new dimension. Where is it? Is it everybody who thinks it's outside the solar system, raise your hand. Everybody who thinks it's on the border, raise your hand. So I held my hand up on both. It's entering a new dimension, and that had less IT on it than you have in your pocket. In fact, thousands of times less. So going towards the new reality, science fiction 10 years ago, reality, as we saw, today. It's driving on Mars. Now, what's science fiction next? What spacecraft is this? Why am I showing it? Because we're enterprise IT.
And just to put this, Just to put this in context, 3 years ago, Tom and I met with the team, the Cassini team, which is basically an orbiter around Saturn at this point. And we started describing to them how we can provision capacity on demand, and we can make our servers. We can have one server right now and 5,000 the next moment. And the scientists, project scientists, looked at us and exclaimed, wow, that's science fiction. These are guys that are running spacecraft on Jupiter, and they're calling cloud computing science fiction. That's really where we're coming from here.
So let's start the journey. That was science fiction. We're going to create this spacecraft called Enterprise IT. How many people are from an enterprise here? Or more, let's say, more than 500 people in your company. Wow, OK, so this is going to be very relevant to you. It's also going to be relevant to all your startups. How many startups do we have in here? Because you're the ones who's going to make it happen. You're going to ride on top of that large infrastructure that you can create and dismantle in seconds, but you're the ones who's going to create the new businesses. That is the new reality. So let's take a look at evolution. JPL is all about evolving. We are nestled in the foothills of California, as you heard this morning. We're into robotic spacecraft. Everything that doesn't have a human on it is a robot to us, whether it be an arm or a spacecraft. You heard about Curiosity. That was just the last of many missions that we've done this year. It's been a very, very busy year. In fact, 10 times busier than normal. So we've had a lot of successes. The next successes will come from faster innovation, less budget, more IT. So here's how we do business today. This is an IT crew, very fine-looking IT crew. We've done the budgeting, we assembled them, and now they're ready to go to work to build that infrastructure. We need to transform that into a way where we create the infrastructure as we walk on it. And what is that? Come on. Cloud computing. So we also have to transform how we do business. It's no longer about coming up with the ideas, getting them vetted, getting the budget, build them. It's about rapid prototyping. It's about trying things and failing. Thomas Edison was asked, how come you failed so many times? And he said, I didn't fail at all. I learned 1,000 ways of not creating a light bulb. And that's the mentality we have to do, and cloud computing will help us get there. So let's take a look at today's reality. Let's see what was science fiction just a few years ago and where we are, and this is all about cloud computing. Our cloud journey started with Jim Rinaldi, who's the CIO at JPL and my boss, said, I'm tired of buying computers. I just want to rent them. He said it in these nicer words, but that's what he meant. How can we do that? And Jonathan Chang, raise your hand, was one of the initial victims. He's a developer. And he said, OK, Jonathan, you can't buy any more servers. You have to rent them from the cloud. And Jonathan grumbled, and eventually he got used to it. And it's been very good. So let's take a look at the experience. Khawaja, how can we try cloud computing immediately and securely? And this is 4 years ago, by the way, when we said, OK, we're going to do this.
So Tom and I work with a variety of missions. We work with a lot of missions across NASA and some agencies actually beyond NASA as well. And in our journey, we come across a lot of prevalent myths in terms of cloud computing. And the number one myth that we hear is that cloud computing is not secure. You can't run sensitive applications on the cloud. And we started evaluating this myth a while ago, in 2008 actually, and we learned some lessons in this process. We read, first of all, from Bruce Schneier that the biggest risk in cloud computing, the biggest fear in cloud computing that the public holds is having to trust a third-party entity. But Bruce Schneier very profoundly asked in that same blog, who else do we already trust? Do we not trust Microsoft with our operating systems? Do we not trust Cisco with our firewalls? It is an important question to ask. It's not something radical to have to trust a third-party entity. What did we do when we trusted operating systems with Microsoft? We evaluated the risks. We evaluated the cost of not doing this and writing our own operating systems. And some people would have argued at the time that that was the right thing to do. But then we realized that we can get a strategic advantage by using these capabilities, and we could mitigate the risks sufficiently to take advantage of these new capabilities. So that gave us some inspiration a few years ago, and we started looking at cloud computing. So we started trying cloud computing in a very open environment. We have a lot of public data. Our charter is to get our data out to you as quickly as we possibly can. So we built a bunch of public outreach applications, and we put them across multiple cloud vendors. So we put them on Microsoft, Google, Amazon, as well as some of our private cloud solutions. And we learned a lot. We were able to train our developers on the new cloud paradigm while learning about the security implications and how to effectively secure applications in the cloud. And very soon, we realized that you can actually do secure computing in the cloud. And Tom will actually go on the record saying that in many cases, cloud computing can actually be more secure than your internal infrastructure.
And you can tweet that.
And the reason why it can be more secure than your internal infrastructure is because of the unprecedented transparency that cloud provides you over your infrastructure. It is the ability to list all of your instances with a single API call. It is the ability to respond to incidents by API calls and saying, plug this firewall hole. It is the ability to define dynamically define subnets that enable collaboration across different networks. It's the ability to isolate machines as soon as you think that they're compromised. And it's the ability to uniformly deploy lots of machines with a single AMI.
So the other thing about cloud computing, so I'm in enterprise IT. I'm here to make your job better. We have to make it simpler. I mean, the future is easy to find, easy to buy, easy to use, and easy to lose. That's not infrastructure. So what we did at JPL is we have a single on-ramp. You type in cloud computing in your browser, and it brings up the CASM, the Cloud Application Suitability Model, which tells you, based on the answers you give to questions, where that application best lives. So it makes it easy, and you can charge a normal chargeback model that we do at JPL. That's important. If you're in corporate IT or in security, if there is a security breach, guess who's responsible? Anybody? Yell it out. CIO. The CIO, the local CIO is responsible, whether he or she knew about it or not. So that's why IT needs to be the enabler, but make it easy to use. And this is one way of doing it.
And when the choice points to a commercial cloud, we also have a catalog of hardened images that our IT security team has built, which allows us to foster adoption of the best security practices. It allows us IT security to provide oversight and guidance as to how to secure your applications rather than our developer going off and installing Linux on a desktop under his cubicle and running it as a server. And by the way, that will never get patched, I promise. So, Tom, how can we try cloud computing for mission-critical operations?
Well, Khawaja, there's a myth that the cloud is not reliable. So what does that really mean? Let's examine that myth. Would you?
So I think actually cloud computing allows us to get as much reliability and availability as we need. And at JPL, our approach is to actually define a spectrum along which we can control the amount of availability for our applications. So let me explain the spectrum to you. If you are running thousands of machines, you will see every once in a while an instance failing. This will happen in your own data centers. This can happen in the cloud. But it's a lot less likely to see an entire data center, entire availability zone fail. It's even less likely to see multiple availability zones fail, but that has happened, right? So if you want the ultimate security, you can build an application with multi-region availability. And the reason why cloud computing is helping you here is because you've got a uniform interface to deploy these applications across data centers around the world. And if you're really good, if you're as good as Netflix, you can actually have a chaos monkey that's a very surly monkey, according to Yuri, who only works from 9 to 2 and randomly turns off your machines to ensure that the developers at Netflix adhere to the best availability practices and their infrastructure is always available. And why not? Why shouldn't we at NASA be thinking like that as well? There are physical aspects of the world that we just can't control. We are in the foothills of Pasadena, which means that we're in fire county. So this is the station fire, which came very close to JPL, within inches of JPL, which meant the whole city was actually evacuated for a while. Now, the scientists running our applications from Cornell or around the world in Spain don't really care that JPL is on fire. They want to get access to their data because they've got a paper deadline, right? You guys remember the angry professors? No, you don't want to mess with them. So we've also started using cloud computing to augment the availability and durability of our applications. In fact, the Mars exploration rovers are archiving dozens of terabytes of data. All the data that we ever collected and sent to Mars through the Mars exploration rovers is backed up today on the cloud through an orchestration process powered by SWF and durable storage provided by S3. But backup is easy, recovery is hard. So we actually also audit these capabilities by randomly picking files, recovering them and checking if they have changed on the system or if we have lost anything. More importantly, in this process, we have built a distributed cron job system. Anybody dealt with cron jobs recently? All right. So the cron jobs are evil because they're so simple. You can set them up and say, OK, every day at 5, run this particular task. And soon enough, in a mission-critical environment, people will come to rely on this file that you're delivering at 5 p.m. every day. And then before you know it, you'll retire that machine. And all of a sudden, this file stops showing up, and you have no idea why. Right? This machine went off, but you're not going to put the 2 and 2 together because you're panicking. Somebody's calling and saying, hey, this file isn't here. Eventually, you'll figure it out, and then you'll go, well, I don't have the script anymore. What do I do now? So with SWF, we have actually built distributed cron jobs that run across multiple machines. It allows us to have this job occur even if the particular machine is down. It also allows us to get a centralized dashboard to see which jobs are failing or timing out so that we're not running across 50 machines. Oh, which cron job is doing this? And what is the order in which things are happening? You can actually very succinctly express complex workflows and see them in a centralized dashboard, and that's what we really like.
And what I really like is there is no people harmed in this process, which means it's inexpensive. So we love Netflix for coming up with the idea of the chaos monkey, because you can build reliable systems out of unreliable components. It'll change the way we write code. That's all right. You guys are coders. You can figure that out. More importantly, it'll make things faster, less expensive, and a whole lot more reliable. So, for instance, how do we go to secure uplink planning? In November 2010, we rolled the dice with John Callis, who's the project manager for Mars Exploration Rovers. And how did we roll the dice? One of the things that we often run into is people said, oh yeah, it's all right for you NASA guys, you have tons of money. We can't afford to do cloud. And that is so backwards. First of all, we don't have lots of money. Second, you can afford it. So what we did in this case, Mars Exploration Rovers were supposed to last 90 days. 8 years later, all the IT systems were full. So we said, OK, John Callis, we can do it inside or outside. Either way, it's going to cost money. What do you want to do? And we did it outside in the cloud. And we saved 1 order of magnitude on cost, and we gained 2 order of magnitudes on response time for mission-critical operations. It's encrypted. It's all that good stuff that you would hope we would do. But it really showed us the value that we can use it on mission-critical computer.
That application, by the way, has got 100% availability since 2010, which is something that we're very proud of because we're using very highly available services in the cloud that sustain AZ failures very, very effectively without us having to do a lot of engineering around it.
But what about high-performance computing? What about supercomputing? Reserved for the rich, no way that college student could use it, right, Khawaja?
Not true. Recently, NASA headquarters funded us to actually evaluate the efficacy of cloud computing for high-performance computing. And we ran some benchmarks to realize that we can run about, for $35 an hour, we could run, for $35 an hour, we can actually run 12.7 teraflops of compute capacity. Put this in context, a top 500 supercomputer is about 50 teraflops. So in today's spot market prices, you can actually provision a top 500 supercomputer for about $100 an hour, right? Now put yourself in the shoes of a graduate student who's got a paper deadline armed with basically a top 500 supercomputer at his disposal with a couple $100 in his pocket. It's going to transform the way we do science today.
And it's crowdsourcing of the best kind. All of a sudden, we can get everybody to participate to build a better government or your own company, whatever it happens to be.
So Tom, cloud computing should be as simple as using a credit card, right?
So in fact, in 2008, it was. That's when we started doing this. And what we discovered is that we are enterprise IT. Not so easy. We can't do credit cards. We do chargebacks. We are a pretty big organization. So how do we deal with that? Well, that's easy. Anytime we need a contract. And to get a contract, we argue a lot.
Anybody got a lawyer at their organization?
Is anybody a lawyer in here?
Oops.
No, that's good. That's good. Is there an auditor in here? Oh, I'm so sorry. I used to say, is there an IT security person in here? And people will go, okay. And I said, everybody else hug that person, because that is your future. The auditors and lawyers, they are our future to really take advantage of this. So thank you for being here. So we did agree on it. It took over 8 months. And we learned a lot. We learned about what matters and what doesn't matter, and we're happy to share those stories. SLAs are almost meaningless for us. If we lose science data that costs millions of dollars to get back, and we get 10 cents on the dollar back, that's meaningless. 3 strikes, and they're out, and we'll go to a different cloud provider. That's how we look at it. So, for instance, we had 100% availability on Mars rovers. It was only advertised as an SLA of 98%. If we were to go and say that we're going to get a vendor that has 98%, we couldn't do it. So we have to think differently. So what we recommend is that you big IT, enterprise IT, create a cloud computing commodity board. And it's the commodity is the important part. Cloud computing is like electricity. You can just buy it if you have a big enough contract. You don't have to argue every single time. And that's what we did. So we actually have several different cloud vendors. Of course, we love Amazon, but we have other cloud vendors too. All right, enough playing. How can we use cloud computing for really hard things, Khawaja?
I don't know, it depends on what the next slide is. So one of the biggest myths that we have come across is cloud computing is only meant for storage and processing. And that's also not true. Sure, we have used cloud computing for radar data processing, where a scientist came to us with a paper deadline and said, well, I started this process, and it's going to take a week and a half for it to finish on my local infrastructure. Can you please help me make it finish faster? So we coded overnight, and then we launched a set of 80 machines in the cloud, and specifically in GovCloud in this case. And 4 hours later, the scientist had all of his results. He had 300 gigabytes of input data, 4 terabytes of output data that he needed to examine just a little part of. We did this overnight. We wrote the code. 4 hours later, we executed the code. It was done, and the scientist got his data and a total cost of $256. That was a real empowerment and basically delivered a big strategic advantage to our scientist who was able to actually make his paper deadline. But again, that's the processing part, right? That's processing and storage. What would cloud do other than processing and storage? Well, the fact of the matter is that the cloud vendors have been in this business of making highly available systems, highly distributed applications, and highly performant applications for a long time, right? And they have basically started to create an ecosystem that will streamline the development of your applications so that you don't have to go figure out how to run a high availability load balancer, so that you don't have to go figure out how to run your own orchestration service and operate it, and you don't have to go figure out how to run your very highly available databases. So for the Mars Science Laboratory, we use a slew of services to expedite our processing needs. So we use SWF for the orchestration, EC2 for processing, S3 for the storage and delivery of the system, SimpleDB to index these plans and images, CloudWatch to monitor our instances and get a text message anytime something funky happens to our system, IAMs, Identity Access Management, to control access to our sensitive resources, and load balancers to develop and deploy highly available applications. Now imagine if you had to figure all of that out from scratch. Imagine the time it would have taken our developers to go figure this out. And by the way, we would have figured it out, but it would have taken us a lot longer, and we probably would have made a lot of mistakes that we don't have to anymore.
And then in addition to that, we would have had to maintain that code. Building something is cheap and easy. The life cycle maintenance is what really costs money. So this is the future, not us not having to develop it. Here's another use case of, so some things are perfect for the cloud, some things just don't fit. And that's what we're about. We're about putting the right thing in the right place. This is the right thing in the right place. It's a spacecraft that once a month will go over the North Pole and look for carbon. Lots of compute power needed for that flight. That aircraft will fly, it'll land. 30 days later, it'll fly and land. So we can spin up lots of computers, spin them down. And it saved 2/3 of the IT cost, doing it that way over what we normally do. This is the future. This is truly the future, the hybrid cloud. So the hybrid cloud means many things to many different people. To us, what it means is that we can spin up a small set of servers and compute tasks in our own environment. They spin up their equivalents in a cloud environment like Amazon's. They do the job using all that infrastructure we're renting temporarily. They spin down, and we have it inside as a backup, should that cloud disappear. So today it's Amazon. It's many different services of Amazon. It could be other clouds too. So when you think about your architecture, think about the hybrid cloud. And we tend to believe that maybe we have a private cloud today, but maybe private clouds are not going to be needed. Maybe they will all be secured by you all and run on a large vendor's infrastructure. Because after all, it's just water. It's just electricity.
And if you're a developer itching to convince your management to try out cloud computing, imagine the use case here. In case the cloud isn't available, we would be no worse off than if we were just relying on the internal infrastructure. But for the days that cloud is highly available, which is almost every day, you can augment your internal capacity and pay only for what you use and get your results a lot faster.
All right.
So we've already talked
about that one. So this little thing called curiosity. You heard about it this morning, and Khawaja is not going to get quite as excited this time, but he's going to talk about what happened. I'll talk about this part. Our world turned upside down. We had 2 weeks. Curiosity has been in plan for years and years and years. We think of everything that could go wrong, and we try to mitigate it. This 2 weeks before he said, okay, this is your Olympics, this is your Super Bowl. You have to stream it to the world.
All right. And by the way, this is 2 weeks, or actually 10 days before the rover actually landed. So every developer at JPL was basically working on, every developer on my team was basically focusing on making Curiosity work and completely oversubscribed. And Brett, can you raise your hand? Brett George stepped in and worked very diligently for the next 10 days to develop and deploy a system that could sustain the bandwidth limitations that we had, the bandwidth constraints and the bandwidth requirements that we had. And we worked very closely in this case to deploy this, this application. We worked very closely with folks at Amazon. In fact, Jamie Kinney and Miles Ward from Amazon were at JPL 4 a.m. the night before landing, making sure that all the pieces were in place and that we could actually sustain this kind of bandwidth.
The paint wasn't even dry yet.
So what did we do? We started with CloudFormation stacks that had layers, a 2-layer fan-out caching architecture tied together with an elastic load balancer, and each of these stacks could do 25 gigabits per second of traffic. All right, well, we needed to do 50, we added another stack. We added to do 75, and keep going. So now we've got 5 stacks that can do 125 gigabits per second of traffic in total. But how do we tie all of these together? Well, we simply used Route 53 and used weighted round robin to actually load balance across the load balancers. And the fundamental advantage here was that we can actually get multi-region support for our load balancers. If you wanted to go really advanced, if we had 11 days instead of 10, we would have done latency-based routing mixed with weighted round robin so that the people in LA go to the elastic load balancer in San Francisco while the people in New York go to the elastic load balancers in Virginia. Right? You can do all of that in a matter of a few hours just by making, reading a couple articles and making a few clicks on your console, and you're ready to go. Imagine what this would have taken prior to having this kind of a DNS service in the past. Meanwhile, Elastic Load Balancer is also monitoring the health of every individual node and taking them out of commission as soon as they stop responding to the health checks. Furthermore, auto-scaling groups are then protecting the number of nodes that are available in each CloudFormation stack, so that if we had auto-scaling groups with minimum and maximum number of nodes to be exactly the same, so we weren't using it to actually scale, we were using it to maintain. So if one of the 40 nodes goes down, it just replaces it with another 40. So we ended up deploying, thanks to Brett's heroic work, we ended up deploying a scalable architecture that could sustain the failure of the entire East Coast and actually many other data centers and still deliver video. So we ended up doing more than 150 gigabits per second of traffic, 80,000 requests per second. In a matter of a couple of hours, we served over 150 terabytes to the public, and we had some very happy customers at the end.
And that's Pete Teisinger and Richard Cook, the project manager and deputy project manager of Curiosity, 2 of the smartest people we've ever met. Now remember all of this, and Brett, raise your hand again. Brett will be the first one to admit he had a lot to learn. He'd never even have a clue how to do any of this 2 weeks before. So he was a little nervous. But thanks to Amazon, it all worked out, and to Brett's hard work. This is Curiosity now on Mars, a self-portrait. And it's healthy. It's looking for signs of life. And we're looking forward to see if it finds it. So cloud computing is now part of everything that we do. 4 years ago, it was cloud computing, the experiment. Today, it's the pervasive cloud. It's part of everything that we do. So what will the future look like? So these may not be having a drink on Mars, but it's really important. And how do you do that? We all talk about disaster recovery. It's damn expensive. So most of us we hand wave at it. Well, all of a sudden, you can do it. You can build it into your enterprise architecture, and you can use Glacier. And you can use things like Panzura. I see the Panzura CEO here, where you make it really, we do use that at JPL, so it looks like it's local storage, you make it simple, and it puts it in the least expensive or most appropriate place. So this is an actual use case, cost modeling, of a real specific use case of storing 70 terabytes of data somewhere for disaster recovery purposes. The red line is Glacier. Now, this is where you developers and smart people come in. It isn't just that you put it there and bring it back. You really have to think it through. It depends on how fast you need it back. So really go through the use case and think about it so you can fine-tune it. And there's different strokes for different folks. Glacier is really good for long-term storage, and it's really good. But if you bring it back all the time, you pay a lot of transfer charges. So architecture, think it through. When you couple that with the new GovCloud, we can have a really secure and ITAR export control environment. So we're quite excited about that. Now, here's another one. What about finding any information at any time? Any information. And what does cloud have to do with it? So we built a prototype. And the prototype, the science fiction is this. You want to be able to find, we're interested in ion propulsion. You want to be able to find wherever somebody said the words ion propulsion, whether it's spoken or in a video or typed. So was that possible? We partnered with Microsoft. They had something in the back shelf. We tested it, and they commercialized it. We can use it. And we ran it through Amazon to get it started in their cloud. And now we built a prototype, a NASA 2. It's just for internal, private, very sensitive videos. Now where we're going to store it. So we were waiting for the infrastructure to spin up, and eventually we just put it into GovCloud overnight. And it sits there, and it works, and all of a sudden we can find those information. The other benefit, anybody heard of 508 compliance? Anybody from the government? 508 compliance is the hindrance to putting videos on. And we know from YouTube generation that videos is the future. Short snippets of videos that tell you everything you need, but they have to be transcribed. So this does automatic transcription. It just comes as part of it. So all of a sudden, by using GovCloud, it's secure. By using cloud computing, we can put it there. And by using actually two clouds in this case, Azure to Amazon GovCloud, it's completely transparent and completely automated. So that is a real key. So what about the workforce? How can you have an unlimited workforce? Well, for us, it's about not having to build it inside, but being able to have an environment where we can bring in lots of other partners. What does that look like? Anybody participated in the International Space App Challenge? All right, thank you. One person. Give him a hero's applause. Thank you, thank you. Anybody ever participated in hackathon? Okay, 1, 2, 3.5, 4. That's really powerful. And what do they all have in common? They're all volunteer. They all use cloud computing, and they all use the latest technology, usually non-structured databases, et cetera. That's our future. We posted 60 problems, and at the same time, on all 7 continents, there were people programming over the weekend, came up with 100 solutions that we now can use. All right, what does SaaS mean? Say it louder. What does it mean to us, Khawaja?
Tom and I stumbled upon a little secret, students as a service. We mentor dozens of students as part of our job to identify the future leaders and identify the next generation workforce. And as part of this, cloud computing involves a lot of prototyping. So we are able to hire these students, and actually one of our students is here in the audience, Ben Schwartz from University of Maryland. And these students are actually providing really compelling results to us in terms of proving the efficacy of cloud computing and then building real applications that we're then immediately integrating into mission-critical applications. So on the screen here, you've got Andres Riofrio and Alex Kern. Alex Kern was a senior in high school, and he worked on the MER backup project that you saw, the data archiving project. Andres Riofrio, freshman at UC Santa Barbara, worked on the CARV project, which is the aircraft that flies once a month. Now, these interns are able to provide real proof to us that we can actually put these applications in the cloud. We get to mentor them. They get to give us real code, and they're really cheap. So everybody wins.
But so this is a case of these high school student and college student giving a presentation. We do IT innovation seminars to all of JPL, not just to the other students. and they just rocked the house. It was fantastic. So students as a service, don't underestimate what they can do, and you can afford it.
Yeah, not to demean our developers, but we actually learn a lot from the students because they have such high levels of energy. And just get Ben started on talking about anything and just see what you learn. Have fun, Ben.
So
Tom, how can we collaborate better in the future?
Oh, thank you for asking. Let me turn it right back at you, pal. How can the scientists collaborate better in the future?
Right, so NASA just funded us to actually build a collaborative environment powered by the cloud. The typical open source model for scientific computing today is that scientists, and by the way, these aren't computer scientists, are getting open source science software in the form of source code, which means that this geologist, physicist, chemist is going to download a binary source code file that's zipped, and then they're going to try to compile it, and oh wait, there's dependencies. Oh wait, the dependencies have dependencies. Oh my god, I got the wrong version. And they've all of a sudden wasted 3 days trying to figure out how to install this software. And in this process, they might have actually broken the other DLL files and the SOs that they have. And they really don't want to be dealing with this. So what is cloud computing doing to help us there? Well, instead of disseminating this software as source code, we're now able to disseminate the software in terms of virtual machine images. This means that the applications can be executed in the same environment that the developer tested and developed in. This means that we have streamlined access to these algorithms and different versions of the algorithms. This means that we have co-located the data with virtually limitless capacity so that scientists are no longer waiting for the terabytes of data to transfer from Virginia back to Pasadena. It means that they can get started fast, they can access data fast, and they can store the results fast, and they can collaborate better than they could ever before.
And if you tie that in with the crowdsourcing, and the students that are getting their PhD somewhere, getting access to the data, that is today's science fiction. It's going to be tomorrow's reality, where we will have many, many more inventions, innovations, scientific results. But it's not limited to science. It's also, travel dollars are expensive. Video conferencing is, at least my generation, not you young people, we have relationships face-to-face. That's how we create trust. So video conferencing is really key. Problem is there's so many of them. So how do you deal with it? You buy the MCUs and that do the translation, or you use the cloud to do it for you. And all of a sudden, it's MCU as a service. I just made that up. But you don't have to pay for it anymore. Or you have to pay for it, but you don't have to buy the big infrastructure. The other way, but you're still tied to a wall for video conferencing. So let's take a look at what we think the future looks like. And unfortunately, you won't hear them. I'll talk over them. But these are two JPL people working. They're two JPL working from wherever they're working, and they're driving the robots. They can see, and people can see them. And they are driving to meetings, and they're participating. People log in when we had some people who were out sick. They could log in. They can drive around themselves. There's a little bit of problem with stairs, but they're light, so somebody can help them.
We're working on a quadcopter model.
Yeah. But it's very effective. In fact, any consultants in here? Raise your hands. OK. The consultants have found they get more face time with their customers when they come in through the robot.
Well, imagine coming in via Skype chat versus, hey, Tom, hey, I need attention right now. Come on.
So if we do it right, our collaboration with video conferencing and robots, maybe one day we could get some help from the locals. And being helpful neighbors, we would help the locals right back.
Disclaimer, these images are not real.
Remember the robot arm taking pictures? Now, how can you easily access it from any device anywhere? Of course, we're talking about mobility. And do we have any mobile developers in here? All right. The future will truly belong to you, and we want you. We build games for everything we do, but it's not real-time games. It's to keep you informed about what NASA does. But we also use things like...
we've got large-scale, high-rise images, satellite images from Mars and the Moon and the Earth even. And instead of requiring the scientists to download the entire 100-gigapixel or multi-100-gigapixel panoramas and models of the terrain, we actually tile these models into small tiles at every resolution so the scientists are downloading exactly what they're looking at, much like the way Google Maps works on your browser or your iPhone. And we're able to do all this processing in the cloud very rapidly without having to worry about the time it takes.
So now we're talking about science fiction. We're talking about the future architecture. And the next 20 seconds will show you what it looks like. So the way this came about was we had one scientist who wanted to buy an iPad. And I said, nope, not going to let you. And he goes, what? I said, I'll buy you an iPad if you can create something mission critical on it. And of course, he did. So what does it mean, though? Think about it. So all the data, I'm going to show you all the data that's stored on about the moon, pictures from the 60s and on. They're in one place, in a cloud. Guess which cloud? Amazon's cloud. And they will access it from any device, a mobile device, anything, Androids, iPhones, et cetera. And they will take advantage of the capabilities of that device, pinching, swiping. All the heavy-duty processing happens in the cloud. When they need more sensitive data, they log in on that device through a VPN into our private cloud. And all of a sudden, you now have the same application serving two different purposes. What happens if they lose that device? You security people in here. Do we care? No, we buy a new one. The data doesn't live on the device. It's just displayed there.
So technically, the data isn't stored in Amazon's cloud. It's stored in JPL's cloud with an extension into external data centers.
Oh, he's smooth. He's the next CTO. So here, he's pinching and swiping on the iPad. He wants to look at it in 3D. This is actually looking at where the phosphorus is on the moon. So imagine the astronaut walking on the moon with any device. And that's very powerful. And it is that fast because we're using Hadoop to slice the images beforehand.
And you can get access to every single image ever acquired for the moon from an orbiter or a lander by going to lmmp.nasa.gov. You can try it on your browser.
So now the final one, can we go beyond software? And of course we can. 3D printing as a service. This was 2 days before this press conference. He had no idea he's going to have to show a model of the heat shield of MSL. So we had our mechanical engineers design, take the model and email it to a 3D printing house that sent it back. So within 2 days, they had several copies of this. So now what we have is we have cheap 3D printers where they can explore, they can come up with ideation, and then we send the ones that are promising to somebody who has a more expensive printer. So all of a sudden, for $200, we can get a really good 3D printed copy. Another version is augmented reality. And who has an iPhone or an iOS device in here? Raise your hand. Keep your hand up if you have Spacecraft 3D downloaded. Okay, very few. Some do. We'll show it in the break right after. It's quite amazing. And it's our way of reaching the public, but it's much more than that. It is, again, the future. It's how we will do engineering. It's how we will build our models, see if they match what was prescribed, be able to interact with it, see what parts came from where, what the failure rates were, et cetera, et cetera. It ties in big data, it ties in cloud, and it ties in the mobile device. So this was doing the spacecraft 3D 3,000 miles apart, where the tag was using video conference. So he's holding Hubble here at Goddard. So now we've taken the journey from science fiction to evolving and what's going to be tomorrow's possibilities. So what we want to do is, what do you do after this? What are you all going to do? Go to happy hour, right? So at one point in the future, we invite you to a happy hour with the locals.
Again, not real.
It is our most capable rover yet. Underground. The ice wine. So thank you for listening to us. And we will be here for a while. We have time for a few questions, I hope. Yes, in